All right. So it's 3:10, so I guess we can get started. Welcome, everyone. So this is our course on modern power systems. This is the first time that I'm teaching this course. I kind of designed it, or been working on it for the last year or so. So it's been designed in a way to essentially explain how our power systems work minus all of the physics power flow stuff. And so if you're interested in that stuff, some of that is taught in our electrical engineering department, but actually Sac State has a really good program, as I understand. But outside of the physics and power flow stuff, there's a whole slew of things about the electricity grid that actually you wouldn't learn in a lot of those classes, and that I will kind of attempt to teach here. And so, yeah, a lot of my motivation behind this class, I've been in the sort of periphery of power systems, or have even kind of worked a lot myself, but a lot of this is kind of just learned through time and experience, and not through some kind of formal class or formal way that I was taught. And so I kind of wanted to offer that to you guys. So jumping right in. So let's get some of the nitty-gritty stuff out of the way. So course logistics. The syllabus, if you guys haven't seen, is all on Canvas. And so I think most of that should be set in stone at this point. I will hold my office hours on Mondays in my office in Gaussy Hall, so room 3120. If this time doesn't work for you, then yeah, just shoot me an email. I'm always happy to kind of schedule a time that that'll work for you if you're not able to make this. I will say, so office hours starting January 26th, which is a couple weeks away. And the reason for that is next week I'm actually out of town, and I'll talk about what we'll do for lectures for that. And then the week after that, apparently Monday's a holiday. But if you need to reach me, just shoot me an email, and I'm happy to meet. Okay, grading. So class participation, 20%, counts both attendance and participation. I'm not going to be a big stickler on this. Just generally, if you're here, it'll be fine. If you're missing a lot, this only will make a difference in if you're right on the edge and you need a boost, right? So otherwise, I wouldn't worry about this too much. Homework, there's going to be 4 homeworks at 10% each. But I am planning, and I'll try and talk about this maybe a little bit later, an optional replacement assignment type thing where we might have some kind of in-class debates. But I'll talk about that more later when I've got that a little bit more fleshed out. And then we're going to have 2 tests, midterm and a final. Both are worth 20%. So pretty straightforward, hopefully. Any questions about that? No? All right. So next week I'm going to be at a conference in DC, and so I'm going to record the lectures ahead of time, and I'm just going to throw them on YouTube, and then you guys can feel free to watch at your leisure. Okay? And I'll still be kind of working and accessible, so if you guys have questions or anything like that, just let me know. All right. No questions about the class logistics? Okay, so motivation and framing. Okay, so why do we care about power systems in the 21st century? Yeah, power systems, our grid has been around for quite a while, but there are a number of kind of unique things happening kind of in this century that I think make power systems I would say, more exciting place to work in. Um, it had been described to me before that power systems is kind of like not a dead end job, but it's like a very steady, easy growing job in kind of the sort of 20th century. But because a lot of the transformations that are happening now, I think it's attracting a lot of sort of interest for people looking for exciting like job opportunities. So I personally, if you don't know, kind of study electric vehicles. And so the sort of interplay between how EVs interact with the grid poses a lot of pretty unique questions and problems. But it's not just EVs, right, that are transforming kind of the load that the grid sees. There's a number of other sort of pushes towards electrification that will ultimately have impacts on the grid as well. Climate change is making a pretty big difference, and in particular, that first picture with wildfires, I'm sure you guys are all kind of familiar with some of the interplay between wildfires and our electricity system, particularly in California, right, where we have been impacted by wildfires that are caused by the electrical system, as well as wildfires that affect our electrical system ability to function as well. So kind of going both ways. And yeah, leading to things like this, kind of harder to see on this projector, but yeah, blackouts in large cities, and we'll talk about some of this in some of the case studies in a lot more detail. And sort of more broadly speaking, there are like these macro drivers of change in the power sector as well. Does anyone know what that top left map represents? Or at least used to represent? So those are, that represents countries that have signed on to the Paris climate agreements, although I guess technically speaking, the US would currently be back in the yellow because of the current administration. But yeah, we can see that those Paris Accords have been kind of driving individual governments to make sort of big changes to clean up the power sector, yeah. That is agreements signed on by essentially the like European Union, so not like as a single country, but as like as a whole, yeah. Obviously, the big push towards renewables, and in the map on the bottom here, this represents states in the U.S. that have made pushes towards adding a lot more renewables onto their grid through a mechanism known as renewable portfolio standards, something we'll talk about in detail a lot more later. But that's essentially saying that, oh, we want some percentage of the electricity to be coming from a renewable source, right? And so many states in the US have those types of policies in place. And then, of course, there are incentive policies that are pushing for the greening of our electrical system. And so billions and billions of dollars, for example, through the Inflation Reduction Act that was passed a couple years ago, that essentially helps subsidize the deployment of all of this infrastructure. So a lot of big pushes and changes in our power systems, which I think is one of the reasons why I think it's become kind of a lot more attractive for people recently. You know, I myself kind of got drawn into this area because of climate change, right? And that's something that is, I would say, yeah, more recent in the 21st century. Okay, and the folks in this room, and a lot of the folks are coming from our energy graduate group. That's inherently a little bit more interdisciplinary, and I think one of the nice things about power systems is that it's also sort of inherently interdisciplinary, and so there's a lot of I think opportunity for folks coming from different backgrounds to kind of interact with the system, right? So engineers helping to design the systems, economists who study electricity markets, policymakers that can shape the direction of the grid, and then if you're really into the environmental science side of things, right, assessing the impacts of our electricity system. So this is just kind of a slice of the ways that we interact with our power systems kind of professionally. So yeah, lot of opportunity across the board. Yeah, so in terms of what we're going to be talking about, so today is more kind of foundational because people are coming from different backgrounds. We just want to make sure that everyone has kind of the same baseline to work with in terms of when we're talking about energy and power. Then we're going to be talking about the grid, basic grid infrastructure, markets and institutions, stakeholders, and then kind of future prospects. This is kind of rough sketch of what we're going to be talking about in this class, and then more detailed version on the syllabus online. Okay. Any questions about coverage or things that you want to see that might not be up here? All right, well, I'm always open to feedback, right? Again, this is the first time we're covering this course, and so if there are particular topics about the grid that you don't think will be covered, you can always feel free to let me know, and I can plan something for that. All right, so jumping into the main piece for today, we are going to be talking about pretty important concepts as it relates to the grids. If this stuff is not familiar for you, you want to make sure you have a good handle on this, because this is kind of a lot of the language of the grid is going to draw on the sort of foundations here when we're talking about energy and power. Okay, so what is energy? Energy is the ability to perform work, which means you're either moving something or heating an object. And there are a bunch of different forms of energy. And in this class, we'll mainly be concerned with kind of the first 5-ish. We're not going to be talking about we're not really going to be talking about elastic energy. We'll do some nuclear, I guess some gravitational as it pertains to things like hydropower. But a lot of it is going to be thinking about like chemical energy and electrical energy. Okay, and so how do we measure energy? There are a bunch of standard sort of units, and we're going to talk about kind of where they're commonly used and what they typically kind of measure. So joules, watt hours, British thermal units or BTUs, calories, and then electron volts. The last two we won't really talk about too much in this class. So who's heard of a joule? Hopefully most people. Yeah, so joule, right? So this is the gold standard. This is the international standard unit for energy, and used basically across any number of applications and fields. Does anyone know what 1 joule represents?
The gram meters squared per second squared.
Okay, yeah. So, so 1 joule is the ability to move 1 kilogram of weight a distance of 1 meter at an acceleration of 1 meter per second squared. It also is the equivalent of heating 1 gram of water by about 1/4 of a degree centigrade at atmospheric pressure. Yeah, so Joule is, again, very widely used. This is probably the most common representation of forms of energy, except in this class, we're probably going to be using joules a little bit less, and we're mainly going to be talking about things in terms of watt hours. And the reason for that is this is kind of most commonly used in electricity, right? And so a watt hour represents the amount of energy used at a constant power rate over a period of time. And so what does that mean? So 1 watt hour is equal to 3,600 joules or 3.6 kilojoules. Does anyone know the derivation for this? Where does 3,600 come from? Yeah, number of seconds in an hour. That's right. So a watt is actually a unit of power, and we're going to talk about what that is in a moment. But it's basically a watt is joules per second. Okay, and so it's joules over time, but we multiply by time, so that time cancels out, and you're left with joules at the end, or unit of energy, which is why watt hour is a unit of energy, even though we commonly think of watts as a unit of power, right? And so you could do the dimensional analysis. So 1 watt hour is equal to 1 joule per second times hour, which is equal to 1 joule per second times 60 seconds per minute times 60 minutes per hour times hour, right? And these cancel out, and that's how you end up with 3,600 joules. And it's a convenient way in electricity to measure things because most things are rated by power, and then we just measure how long something is operating, and that lets you just call out essentially how much energy is consumed by saying the number of hours, as opposed to doing this sort of translation into joules every time. Okay, and so this is a picture of a meter, and you could just go and read this to basically see how much electricity or energy is consumed by whatever this meter is measuring, probably the electricity consumption at a household, right? And that's going to be in units of kilowatt hours. Yeah, and so watt hours, different way of measuring energy. Usually when we're at the household level, you're talking about kind of in the kilowatt hour sort of range. Once you're bigger and you're talking about like power plants, you might be on the megawatt hour, gigawatt hour operating range. And then when you're talking about sort of larger scale like economies, energy consumption, you might be more on the sort of terawatt hour range. Okay? Yes?
Do you have like a table that can be used as a reference for like when a small nuclear power plant calls out, oh, we're going to be generating 100 megawatts?
Yeah, so
we're going to compare that to everything else, as well as how many, I don't know, households they'll fulfill?
Yeah, I have a little thing that we'll do in just a second on that. Okay, so we'll revisit that in just a moment. The other units of energy that I'll kind of briefly talk about, so BTUs, so British thermal units. So this is commonly used to measure energy content of fuels. Probably most relevant in this class when we're talking about the sort of original form of the fossil fuels that are being used as inputs into power plants, right? And so when we talk about like coal or natural gas, oftentimes they are described in terms of the energy content of the fuel as BTUs. So 1 BTU is the amount of energy used to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So it's kind of like an imperial measure of energy. Yeah.
When you say energy content, you mean like how combustible something is?
Yeah. So the way that you would measure it essentially is you could take any combustible object and then you would put it into there's a couple different ways, but it should represent the like energy content that is contained in the like chemical bonds of that fuel. You can imagine it actually can have a range depending on the way that in which you combust it. For like foods, you would put it in like a bomb calorimeter. You would burn it and then see how much energy is released. For fuels, I'm actually not sure exactly how they do that measurement. You could do it in a bomb calorimeter, but I don't think that's how they actually do that measurement. But yeah, it should be representing the chemical energy content of that fuel. So 1 BTU is roughly 1,000 joules or 1 kilojoule. And for example, in natural gas, it's commonly used to describe the energy content. So an MMBTU, which is the most common way that you're going to see this being described in this class, is 1,000,000 BTUs, and 1,000 cubic feet of natural gas is equal to 1 million BTUs. And then there's a different unit called a therm, which is 100,000 BTUs. So 100 cubic feet is 1 therm. And the last one, we won't really use this that much in this class, but a quad is 10 to the 15th BTUs or a quadrillion BTUs, and that's used particularly in the US because we still use imperial, and that represents annual energy consumption at like large scale economy size. Last one, just for kind of fun, calories. We won't, I guarantee you this is the only time you'll see calories in this class, but energy units, you guys have all seen a nutrition facts label before, hopefully. So calories are used to measure the energy content of foods. Similar to BTUs, but in metric. So this is the energy required to raise 1 gram of water by 1 degree Celsius at 1 atmosphere. So if you remember back to joules, a joule was about a quarter of a degree Celsius. So 1 calorie is about 4 joules, a little more, right? Because it's 0.24. And then the only thing I'll mention about this is that what you commonly see on these labels is not actually a calorie, it's a kilocalorie. So these food labels are actually thousands of kilocalories. Or sorry, thousands of calories, aka kilocalories. Okay, so this is maybe what you were referring to. It's not an elegant table or anything, but to provide some context, right, we want to do some order of magnitude estimations. So I would like you guys to guess the energy content of these things. You can kind of just yell them out, and we'll do order of magnitudes, right? So you don't have to be that exact. You can say between 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, and so on. And you can use whatever units that you want, and then we can all just convert to joules, right? If we need to. Okay, so one meal. What would you guys guess the kind of range is in terms of order of magnitude for energy content?
500 to 1,000.
Yeah, so we're saying on the 100 to 1,000 order of magnitude range. Yeah, most people are hopefully agreeing with that. I hope none of you guys are eating 10,000 calorie meals that often. That would be very impressive. And so 100 to 1,000 kilocalories, not calories, right? Because it's actually 1,000. And I kind of use the same 100 to 1,000 kilojoules, right? Because it's only off by a factor of 4, so it's within what we would describe as kind of the same order of magnitude. Okay, so what would the energy content of the human body be? If you took a human body and you put it in a calorimeter and burned it. Yeah, 100,000. So 100 to 1,000 megajoules. So 100 times bigger. So it's actually, your estimation would be kind of on the lower end, but yeah, that's right. Okay, what about a 1 kilogram lump of coal? What do you guys think? 20 megajoules?
Oh, wait, no. 1 kilogram.
Any guesses?
Kilojoule?
Kilojoule? Okay. Yeah, so it's about 10 to 100 megajoules, so you're right in terms of the sort of order of magnitude. So if you burned a kilogram of a kilogram of coal, you would get roughly 100 times more than if you were to burn like a meal, right? So yeah, the energy content is actually pretty high, right? It's like this compressed, pressurized carbon content. Okay, what about a gallon of gasoline? What do you guys think? So it's about 100 megajoules. So it's kind of on the same order of magnitude of the kilogram of coal, but because we're using these ranges, that's kind of wide. So the kilogram of coal is kind of more on the 20 to 30 megajoule range, and the gallon of gas is going to be kind of the upper end of that. So closer to about 100 megajoules, about 100,000 BTUs, right? So these things are kind of comparable in fuel content. Right, a couple kilograms of coal is going to equate to what you'd get out of that gallon of gasoline. Yeah, and so maybe to put this in some perspective, right, when we think about the energy content that we can derive from some of these fossil fuels relative to, let's say, a renewable resource such as solar, right? So if I were to take sunshine sort of directly going onto the ground, and we're not doing any conversion efficiency losses as it goes onto a PV, just what's the energy content of those photons hitting the ground. How much energy do you guys think would be if we shone that sunlight on the ground for 1 meter squared for an hour? Yeah.
Let's say, yeah, it's kilowatt, so 1 kilowatt, or 1 kilowatt hour, which would be, I don't know, several 20
Yeah. That would be an order of magnitude 20,000 joules lower. But I think your
I think I dropped a
conversion.
zero somewhere.
No. You went the opposite way, right? So, kilowatt hour. When you convert to joules, we should be multiplying by 1,000. Yeah. So your first estimation was correct, right? Because you multiply by 3,600 for watt hour. Yep. Okay. Oop. No one saw that. EV battery. What do you guys think? Anyone have an EV? Does anyone know what range of battery sizes are in modern day electric cars?
400. 40 kilowatt hours.
Yeah. So that would be a smaller-ish one, but we would say probably on the order of like, 40 kilowatt hours up to about 100 kilowatt hours. So in that order of magnitude, which would translate to 100 to 1,000 megajoules, right? And so 1,000 megajoules is really kind of on the upper set size of the battery. And if you think about what that equates to in terms of gallons of gas, right? But that's something like 10 gallons of gas or so. Yeah.
What do the semi-trucks have for kilowatt hours? Because
Oh yeah. Those are a little bit bigger, so a couple hundred kilowatt hours. Yeah.
how do these compare to amp hours? Like the battery capacity sort of.
Yeah. Oh, I always forget the conversion.
How amp hours converts to watt hours depends at what voltage you're
Yeah.
outputting.
Yeah.
So,
What's the
I got beef with amp hours.
Yeah, they always report like phone batteries in amp hours, and I have such a hard time like doing the conversion. In terms of like,
Over to watt hours.
huh?
They're very, very slowly moving over to watt hours.
Yeah. Sometimes you'll see newer ones have the label for both amp hours and watt hours, and then they have to have like the voltage thing. But I think in terms of watt hours, no, I'm not even gonna guess. I did this math at some point, but yeah, I don't remember. I'll look that up and let you guys know. I can add that here next time. What about how much energy does a household use in one day? Any guesses?
24 kilowatt hours.
Sorry?
I said like 24 kilowatt hours.
Yeah, that's right. So we roughly say that the average power consumption is about 1 kilowatt, so averaged over a day, 24 kilowatts. So we're saying the 10 to 100 kilowatt hour range, which is 100 to 1,000 megajoules, right? And so we can say approximately that if you were to able to extract all of the energy out of like a kilogram of coal, right, without any conversion losses, that could power one household for one day. But because of the conversion losses, it'll be a lot less, and we'll get to that. Okay, just for fun, nuclear explosion. Any ideas? You can just throw out some big numbers. See if.
24 therms.
I don't want to do that math. Okay, it's 10 to 100 petajoules, depending on which nuclear bomb you're talking about, because they actually vary quite a bit. So 10 to the ninth, or to the range of 10 to the ninth, or to 100 times 10 to the ninth megajoules. Yeah. So if you were to do that conversion, you divide by, let's say, 1,000 megajoules. So this would power something like on the order of 100 million homes for a day. There's a lot. Okay, any idea about how much energy content the United States consumes annually?
Like what? 800 kilowatts.
800 gigawatts.
80.
That's a unit of power.
Oh,
Gigawatt hours, okay. It's actually quite a bit more. So exajoules, so that would be terawatt hours. So we're talking about on the order of like 100 terawatt hours. Yeah, so 100 quads, which is that unit that's related to related to BTUs, but we'll think of that. We'll go back to the joules to kind of default. And then worldwide annual consumption, any ideas? So if the US uses 100 exajoules, yeah, it's on the order of magnitude kind of larger than that. So 100,000 terawatt hours, and we equate that to, in the range of, 100 to 1,000 exajoules. Okay? Yeah, so this stuff, okay, I don't expect everyone to be able to rattle off all these numbers, kind of, without looking them up. But what I would say is that for some of these fuels and things like that, we ought to get a little bit more familiar and comfortable with kind of the ranges of energy. And that, I think that'll be intuitive as we kind of give lots of these kind of examples throughout the course. So we'll be building up our intuition for the couple one of these that kind of matter more in power systems. And then as kind of a breakdown, this slide shows the energy consumption by source and sector. And so on the left are kind of the input fuels, so petroleum, natural gas, renewable energy, coal, and nuclear. Not all of those things are going to make electricity, right? And so this kind of shows how that's broken out. And the piece that we're really going to care about is all of the sort of inputs and outputs of this piece. Okay. So the electricity is kind of the intermediary where we transform our fuels into this other form of usable energy that then goes to different end use sectors, right? So transportation, industrial, residential, and commercial being kind of the four end use sectors that we typically talk about in these kind of diagrams. Okay, any questions? All right. Let's do, let me see here. Why don't we actually take a 5-minute break here? We'll get a little refresher. Yeah, and we'll do, start again at 53. Okay, we'll get back into it. So that was our kind of discussion about energy, and now we're going to jump into power. Power and energy are not the same thing. So when we think about this from a physics perspective, right, power is the rate at which we do work, or it's energy over time. And so all of the stuff that we've just been talking about, if you divide by time, then you are now in sort of the power territory. So there's two main units of power that we'll talk about. So watts and horsepower. We won't talk too much about horsepower in this class. It's mainly going to be with watts. And so a watt is the SI unit for power, and it's pretty simple. It's just 1 joule per second. Okay, and so in this power systems class, right, we're mainly going to be using this unit, and it's commonly used in electricity to describe things like the capacity of a power plant. And so if I were to say that a power plant has an installed capacity of like 10 megawatts, what does that mean? It means that it is physically able to produce up to 10 megawatts of instantaneous power. So it can produce 10 megajoules of energy per second if you like turned it on all the way. And we'll talk more about kind of the nomenclature a little bit later, but this is kind of just as an example. Yeah, horsepower, yeah, kind of just for fun. We won't use this really that much in this class. It's used to often describe power for engines and mechanical power. 1 horsepower can lift 75 kilograms, 1 meter in a second. And unfortunately, there's actually an imperial and a metric version of a horsepower, which equate to different amounts of watts, slightly different. But we won't need to worry about that. And then my kind of favorite fact about horsepower, does anyone know what is the peak power production of 1 horse? No, it's actually about 15 horsepower. So it doesn't translate very well when you think about it that way. It actually has to do with kind of the average power output of a horse, but yeah. Horses provide more than a single horsepower. Okay, so we're going to do a similar exercise now. Can you guess the power? Okay, so what do you guys think for a light bulb? Maybe you're kind of most familiar with this. Yeah, so it depends, right, on the type of light bulb. So incandescent, I think I'm hearing some people say like, yeah, between 10 to 100 watts. That's right. I think I probably need to update this slide because modern day lights are a lot more efficient. If we're talking about LEDs, you're probably more on the order of 1 to 10 watts. So that's actually a pretty big difference as it pertains to power consumption, right? Maybe 10 to 100 times less power consumption. Okay, what is the power generated from, let's say, someone who's exercising? Does anyone have any ideas? Yeah.
100 to 1,000, I guess.
100 to 1,000, but on the lower end. Yeah, so I made a little narrower range so as not to confuse people. It is on the 100 to 1,000 in terms of order of magnitude, but we're really talking about like 50 to 150 watts. Yeah, you can, if you want, you could try and like there are some of these these power meters, or you've seen some videos of people trying to like power certain appliances, right? And you can only do that for so long for some of those upper like couple 100-watt ranges. Okay, I assume everyone here has used a microwave before. How much power does a microwave use?
15,000.
Yeah. 1,000-ish watts, right? Depends on how strong your microwave is. Okay, how much power does a solar panel produce? Let's just say a sort of generic solar panel that you might see on top of a roof.
800 watts per meter square.
Yeah, so on the order of 100 to 1,000 watts, and then if we're talking about just as a sense of scale, if you think about the like really large solar fields, like out in the desert, we call solar farms, right? Those might be on the order of like hundreds of megawatts for very large ones. I probably wouldn't say. Yeah. Gigawatt size solar farms probably exist, but are pretty rare. Those would be pretty stupendously large. Yeah, you're more on the sort of tens to hundreds of megawatts. Average household, so we just talked about this, right? So the energy consumption was tens of kilowatt hours, and the general thing that you hear is the average household in the US at least consumes about 1 kilowatt of energy, or uses about 1 kilowatt of power on average. Okay, what about a car engine? What do you guys think? You can do this from horsepower, and then you can translate it, and then we can translate it into watts if we need.
120 kilowatts.
Yeah, so in the hundreds, right? And so, yeah, in that range, 100 to 1,000 horsepower. Usually most cars are going to be on the like 100, 200 horsepower, and then you can do that translation to kilowatts. But yeah, there are some cars that get up that high. Okay, wind turbine, any ideas? 10 megawatts would be pretty big.
1 megawatt.
Yeah, more like one megawatt. So for the onshore ones, which are the ones that we see on land, the quite large ones that you see are typically on the order of like 1 megawatt. Now they're getting slightly more efficient, slightly bigger, so like 1.5 megawatt. The really, really big ones that have blades that are like more than a football field length, those are the ones that we call offshore, out in the ocean, and those can be, so the big ones used to be 3 megawatts, and as I understand, there are now as large as like 5, 6 megawatt wind turbines. It's very, very big, yeah.
How do they get that power onshore? Like,
We-
do
we'll-
they have a substation that gathers all the power, and then, or does each turbine have their own?
Stay tuned to find out. That'll be on, that's going to be the online lecture on Tuesday. Yeah. Yeah, we'll talk about all the sort of infrastructure that's connected to that to make that work. Natural gas plant, any ideas?
100 to 1,000.
Yep, 100 to 1,000 megawatts, I think is kind of the typical. So I have it as 10 to 1,000 because we actually do see that range. Very, very small turbines can be in the like tens. That's going to be pretty unusual. Very, very, very large ones that actually typically are probably going to have more than one turbine might be up to the gigawatt scale, but that's also very unusual. Your typical natural gas plant is going to be on the order of like a couple hundred megawatts on average. Okay. What? Sorry. Yeah.
Like jet engines fall on that lower end, sort of. Or maybe
Yeah.
lower even.
Yeah. Yeah. So in fact, I'll mention this on our lecture on Thursday when we talk about some of these fossil fuel plants. But yeah, the turbine. A gas turbine on a jet plane is basically the exact same thing as what you would find in a power plant. You could just take it right off and throw it into a power plant, and it would operate just fine. You probably couldn't do it in reverse because of like all the aerodynamics that they put on the shell and everything. But yeah. Okay. Coal plant. What do you guys think? Yeah, so this is more on the like 100 to, so I put 10,000 megawatts. There are no, I don't believe there are any coal plants that are that big, but there are some coal plants that might be a little bit larger. The kind of largest coal plants might be like 2 to 3 gigawatts. Okay, so that's 2,000 to 3,000 megawatts. You aren't really gonna find smaller coal plants that are operating in the like low hundreds. Kind of the smallest, normal size coal plants are gonna be on the order of like a couple hundred megawatts and up. Yeah.
Is this counting for like, is this per turbine sort of?
It would be for the whole plant.
Entire plant?
Yeah, because sometimes they might have multiple turbines, and I don't think you have more than one boiler, but yeah. Nuclear plants, any ideas?
Half a gigawatt to 2 gigawatts.
So, yeah, I would say more on the upper end of what you're describing. So I think there are some smaller nuclear plants that are like in the upper hundreds. Are you thinking of a particular one that's when you're saying half a gigawatt?
Just for a policy class, I did a deep dive into small modular reactors.
Ah, okay.
Like the
Yes.
cutoff there is 300 megawatts. Above that, it's considered a large plant.
Yep. So this definitely does not include small modular reactors. That is a different, I would kind of form factor of nuclear, but yes, those would be kind of on the like lower hundreds. Most times these nuclear plants, just by the sheer momentum of the way that they operate, you wouldn't find smaller units that often. So I would usually think kind of the smallest in the US that you're gonna find is probably like 800 plus. Most of them are gonna be 1 to 2 gigawatts. Yeah, and so, again, we don't need to be super precise here, but as we think about natural gas to coal to plant, the ways in which they operate kind of dictate some of the sizes, and as a result, kind of natural gas tends to be the smaller of the three, then coal, then nuclear. Okay. California. Who knows what the peak California power demand is? Any idea? Yeah. Yes. All right. Very good. 50 gigawatts. 52 is very precise. That was September of 2021 when we hit that limit, and then everyone got that. Who was here? Who was in California at the time? Yeah, you got that text message, right? That said, "Stop using power." We'll look at that later.
Where were you in California?
Yeah. Well, who grew up in California? Is anyone? Yeah. Okay. A bunch of you. You guys remember back in? Okay. Wait. I might be dating myself. Like back in the like late '90s, early 2000s, there was the whole like flex your power thing. You guys remember that logo? Maybe it's just because I'm getting old.
There was a light switch.
Yeah, that little light switch thing. Yeah. So that actually still exists today. It's there's like programs that are extension of it, but anyways. Okay, total worldwide installed capacity. Any idea? If you took all the power plants across the whole world and you just added them all up, what do you guys think? 1,000 gigawatts? No, not bad. So 15,000 gigawatts-ish. Yeah, a little bit higher now. So I made this particular slide a couple of years ago. So cool. All right. So that is our overview and sort of context of power. And again, don't need to memorize the stuff, but some of these you should internalize a little bit and get kind of familiar with. Okay, so we're going to jump to talking so kind of briefly about sources and forms of energy. Um, right? So primary versus secondary energy. Primary energy is energy in its original form, sourced directly from nature, and so all of these things. So coal, natural gas, crude oil, solar, wind, hydro, nuclear. These are all things that you could go out and like find in nature without having to like necessarily change the chemical composition of, right? So I think a lot of these folks are familiar with. Crude oil would be the one that would be maybe slightly different in the sense that the secondary energy form of that isn't electricity. Oftentimes, right, we're refining that into like gasoline or diesel, which is a secondary form of energy derived by transforming these through some kind of typically chemical transformation process, right? So things like electricity, refined fuels, and hydrogen, so refined fuels would be like gas or diesel, are coming from the processing of primary energy. And we'll talk about this more in detail, right? But hopefully folks are familiar, right? So when we talk about something like coal, starting with the energy mainly in its chemical bonds, we change that into thermal energy as we combust it in a boiler. We translate that heat energy into mechanical energy in a turbine, which then produces electricity. And we'll again talk about this in a little bit more detail later. But the thing to note here is that every step loses, and I should be a little bit more accurate here, useful energy, right? Because we don't actually destroy energy. We can't really destroy energy, but what we lose is useful energy, typically in the form of heat, right? We are better able to take advantage of like electrical energy rather than heat energy to provide like end use services. So every step, you're losing a little bit of energy as you translate to these across these conversion pathways. Okay, any questions about any of this? Great.
I have one question.
Oh, yes.
How you measure the efficiency loss on the boiler to the turbine?
So you can measure kind of what you put in with what comes out, and you compare the two essentially. That's a lot of the ways that these efficiencies are derived. In some cases, there are like a bunch of intermediary steps. So going from like coal to electricity, we usually just think about like the energy content of the coal versus the energy content of the electricity, and then this stuff might not typically be measured unless you're doing some kind of like specific research there, right? And that way it's a lot easier because we know like the energy content of these things. So this is more to point out that those losses happen, but that the actual measurement of them, I would say, is less important for some of the intermediate stuff, because it's like, well, okay, you lose energy in all of the like mechanics of the power plant, but then the ones that you really care about where the conversion losses are happening is like during combustion, and you're trying to make certain parts of that more efficient. That's when you would like really hone in on those exact numbers. But yeah, generally speaking, input, output, compare the two. That's how you get the efficiency numbers. Okay, I realize I included kind of a redundant. This is a similar diagram as before, but actually one of the nice things about this one is that it actually shows you the efficiency losses at every step. And so that's the gray piece up there. That's what we kind of end up losing to, wasted energy. And most of that is, right, like heat in combustion. There is some losses that happen in like the transmission and stuff like that, and we'll get familiar with those numbers as well. But the majority of the energy losses in our electricity system is like heat in combustion.
It's hard to read the bottom, does it say where like the other 6% goes? Like, or
What-
am I just not?
What, 6%?
It's like, it doesn't add to 100, so it's, I don't know if it's interesting.
Oh, rejected energy and energy services. Yeah, well, this is not a percentage, this is by this is the total quads. So this should add to 93.6, yeah. Yeah.
That's exactly what I thought.
All good. Yeah, interpreting these charts on the fly is not always straightforward.
And there's that whole body of fine text at the bottom that describes the limitations.
Source, Lawrence Livermore National Lab, October 24. Data is based on DOE, EIA, and so on and so forth. Yeah, it's just like little descriptors. Okay. So that wraps up our discussion of like energy and power. If there are no more questions about that, we're going to end the rest of today talking about basics of electricity without any math, which will be interesting. So who here has taken either like some physics E&M class or some class in electrical engineering that would make you familiar? Who's familiar with like circuits and how they work ish? Okay, yeah, just wanted to get kind of a sense here. So I think the easiest way that I can kind of describe the way electricity moves in a circuit is an analogy with water in pipes. Okay, this analogy does start to break down at some level, but for a lot of the understanding that we will need for this class, it does a pretty good job. Okay, and so there are a couple properties of electricity and the way they move in circuits that we need to become pretty familiar with in this class. And so three of the four things, voltage, current, resistance, and then the last one that I'll mention is power, and we'll talk about that a little bit more in just a second. And the analogy here, so voltage is kind of like water pressure, okay? So if you imagine water flowing through a pipe, right? If you increase the voltage, or you increase the water pressure, what happens?
Drives flow in the direction pressure decrease.
Yeah, so, yep, that's right. And also, that can affect kind of the amount of water that flows through, right? Which is described as the current, which is your water flow rate. So that's the actual amount of water that's flowing through your pipe in any given moment. And then the resistance is having to do with the kind of how hard it is for electricity to like travel through the wires. Or in other words, you can think of it as kind of like the size of the pipe or the friction of that pipe. So there are certain things in our electrical system that essentially add pressure, right, that like pressurize the water or increase the voltage of electricity. In a basic circuit diagram, we often look at that as like a battery. But there are a number of, let's say, hardware things in an electrical system that could help to increase that pressure or increase that voltage. And then that is what essentially gives us the ability to move the water or electricity through the pipes. And the reason why we do all of this at the end of the day, right, is to essentially be able to use that electricity. So end use of electricity introduces like friction, and so that's represented as a resistor here in this circuit diagram. So this might be like a light bulb. And so when you use up the like water in the system, right, you're like decreasing the pressure, and so that like drops the voltage. And so you can kind of, in a very simplistic sense, continue on with this sort of water analogy to kind of understand the basics of electricity as it flows through these circuits. Okay. Any questions about that so far? So why is it that we care about voltage in these electrical systems? So it turns out that there's, so Ohm's law, this is like a basic physics thing in E&M that you would learn. So voltage is equal to current times resistance, right? And so it's like the amount of water flowing, how hard it is to go through the wires will tell us the kind of pressure of the water in the system. But there's another kind of formula that we care about a lot in these power systems, which is the power loss formula. So power is equal to I squared times R, and that describes the functional relationship between the amount of water flowing through your pipes, how resistive those pipes are, and the loss in power as a result of moving through those pipes, right? And so as you transmit electricity from one point to another, you will lose power because of the resistance in the wire. So the way that I kind of describe, that I'll kind of show how this happens, right? You could have high current moving through a pipe at low voltage, right? And so that gives you an equivalent amount of electricity as, let's say, something that has low current but high voltage, okay? And which one of these would we prefer in order to reduce our power loss? What do you guys think? Yeah, so high voltage, low current, right? Because the I squared contributes a lot to our power loss, and so that's kind of the fundamental reason why our electricity system has things operating at sort of different voltages. Okay, and so
I really like this. It's like you can imagine like a big diameter pipe.
yes.
Then you have less water in contact with the edges, less friction, less losses. Versus a skinny pipe with like really fast moving water, and a lot of contact with the edges.
Although
Does it break down?
I'm seeing how my analogy might be confusing a little bit. So what you're saying is correct as you refer to the size of the pipes, but the more important thing is that the amount of current going through, let's say if you have equal-sized pipes, the current going through them, you want that to be as low as possible because the I squared makes a bigger difference than, well, this is all relative terms, right? But I squared is going to explode in terms of power loss compared to your R, because the R is linear, whereas the current is squared. So whatever you can do to reduce the amount of current is preferable. And because power is related to both of those terms, if you jack up the voltage, then you can get by with doing lower current. Yeah. Oh, I should probably have that in here. But there's another equation. Power equals I times V, right? And so you could have low current and high voltage for the same power, or you can have high current and low voltage for the same power. But when we're transmitting it across these larger distances, we would prefer I to be low because of the power loss law. And when we think about the voltage of the grid, this is the reason why when we have these giant transmission lines, right? So these are the big metal towers that you see on the freeways that transfer electricity these really long distances. We want the voltage to be as high as possible so that the amount of current that you're sending through them is as low as possible so that you have less power loss, okay? So you can think of like these transmission lines as kind of like extremely pressurized water. So this would be like water coming out of like a fire hose, right? But for our houses, like, can you imagine if the water coming out of your sink was like a fire hose, right? It would be unusable. And so in a similar way, we have to, in order to make the electricity usable and less dangerous, right? You want more of like a garden hose type of pressure as opposed to like a fire hose type of pressure. And so as we get close to the end use, the voltages will drop. And we want to do that kind of at lower distances as possible to, again, reduce the power loss. And so we have, at the highest when it's transmitting, we are going to have our highest voltages, and then in the local distribution system, we'll have kind of our medium voltages, and then out of our outlets here, right, we're going to have our sort of lowest safer voltages. Any questions about that? Okay. Yeah, so now we're going to talk about alternating current versus direct current without any math, which is going to be, yeah, if there was like an electrical engineer in here, they'd be kind of yelling at me that, but okay. So on the left side, we've got direct current. On the right side, we have alternating current. So again, current, think of that as the amount of water flowing through the pipe. So who can tell me what that is up there? What that picture is? Water tower, yes. How does a water tower work? Does anyone know? Yeah, so let's say we were to have a blackout in Davis, okay? And then you guys go and you like try and turn on your lights. Doesn't work, right? Hop in the shower and you turn on your water, or you want to like wash your dishes or something during the blackout. Guess what? Does it work? Yes. It does work. Yes, for a while. And why does it work? Gravity. Exactly. So what's happening is water towers hold water at a high height so that you can take advantage of potential energy to pressurize our water systems, right? And so you can think of water just continuously kind of pushing out into, it's all the water in the tower is essentially pressurizing our water system. Otherwise, we would need electrical pumps, right, to continuously pressurize that water. And so when you turn on a faucet, you have a continuous stream of water. So this is very much akin to what a direct current is like. It is essentially providing a continuous stream of electricity. And so sources that produce direct currents would be something like a battery. And so this is kind of the closest analogy that I can think of to describe the way direct current moves through our electricity system. Okay, what is this picture? Does anyone know? A water pump. Who's operated a water pump before? Okay, when you start pumping, what happens?
Water comes out, but like at intervals.
Yeah, so you're pumping this handle, right, up and down, and water will start spurting out. And eventually, if you do it fast enough, it'll look like a continuous stream, right?
You gotta be really strong.
Yeah, exactly. So in fact, the vast majority of our electricity, any electricity that's being produced out of a turbine, actually looks like the water that would be coming out of a pump. Okay, it is in this alternating current, and the physical reason for that is in the way that generators work, right? So you have you essentially are moving a coil through a magnetic field in some way, right? And so the magnets, as this coil is closest to the magnet and it's moving, it will produce kind of the highest voltage. But as it spins and moves away, that voltage will drop. And so that is essentially what's creating this alternating current. And again, if you produce it fast enough, then it'll look like a continuous stream. But what's really happening is very much akin to what would be happening as you pump a water pump. It's essentially coming out in spurts. There's a frequency at which this thing happens, and if you slow that frequency down enough, and you were to like send that electricity through like a light bulb, you can actually see the light bulb will flicker on and off at the same rate as that electrical frequency. Okay, does that make sense to everyone? And so the reason why this is important is that AC and DC are not sort of directly compatible. You can't just like mix them in the same circuit. And end uses of different devices might use things at different different types of currents in AC versus DC. And so you'll actually need you often will need like converters in order to change current from AC to DC. That's actually the reason why, for example, let's see. Yeah, so this is like my laptop block, right? And so why is it that some things that you plug in are just those like small typical plugs, and why do some things have these like blocks with them, right? Yeah.
I mean, your laptop has a battery, so it wants direct current.
Yeah, exactly. So
Some fans might want AC current, some of them might want DC.
yeah, and so you can actually tell from your end use appliance if they have these little block things that actually they're doing a conversion into DC, because everything out of the walls is operating on alternating current. Okay. And so that's going to come into play as we talk about specific hardware and infrastructure in the grid system. But this is kind of the reason for that is the differences between AC and DC current. Okay? Any questions or confusions about this? Yeah.
Is there a reason for picking one over the other for like the typical outlet, not for instance?
Yeah, so because power is generally produced as AC, so anything that spins to make power, it was kind of deemed lowest cost and easiest to just keep everything in AC as opposed to DC. Now that is a debate that continually resurfaces because there are actually a lot of benefits to doing things in DC. And actually people have, I had a colleague in grad school who wrote a whole dissertation about using DC primarily in residential systems. I think one of the reasons why this has started to become a more interesting debate, can anyone think of why DC is maybe starting to become discussed more as kind of the default for residential systems? Yeah, because of solar panels, right? So I said the vast majority of power is produced by AC, but solar is not. The solar doesn't use something to spin. All the power produced out of a solar panel is DC power, and so if you've got all that rooftop solar generated locally, in order to power your home, right, you got to convert it back into AC, which can be expensive, inefficient, blah blah blah. Yeah.
AC, I think, also has the advantage of you can transport quite a lot of power with just 2 or 3 wires with multi-phase electricity.
Yes.
And then smush it back together where you need to use it.
Yes, exactly. So for the transfer of electricity, so I think a lot of what I was discussing is about AC versus DC at the end in the end use system. For the transfer, it's this is the like Tesla versus Edison debate, and I think AC pretty handily won out for the reasons that you're talking about.
For off-grid applications, it sounds really interesting on like a DC
Yeah.
system for a house.
Yeah, but for transmission of electricity, AC I think is pretty clearly the winner. Although even there's like some like DC tie things that people are talking about now. But okay, I mean, we're not going to touch on that too much. And I think part of the reason for that is a lot of the interesting stuff about that gets into some of the like mathiness of the like 3-phase reactive, power stuff, and why you're physically able to separate that. So we won't get into that other than to say that yes, that's right. For AC, there are inherent advantages in AC for transferring electricity that has led it to become the sort of dominant way we do things. Okay. Electricity as a commodity. So when we think about goods and services, does anyone know what a commodity is? What is a commodity?
Bought, sold, used up.
So commodity is a particular type of good, which is sort of completely interchangeable, right? And so, if I were to get shoes, we don't consider shoes necessarily to be a commodity, right? Because there is some difference between like Nike shoes and like Adidas and whatever, right? But for something like water or for something like electricity, it doesn't matter that a natural gas plant or a solar plant or a wind farm produce the electricity. The like physical electricity that we consume is the same everywhere, right? And so that is one sort of interesting aspect that we'll need to kind of reconcile later on in the class. That although electricity is produced by very many different sources, because it is a commodity, it operates kind of fungibly in kind of one market, right? There isn't anything unique about electricity produced by one source versus another. There is something particularly unique about electricity itself as a commodity, is that we think about electricity as something that can't really be stored. Okay, and so yes, there's electrical storage, and we're going to talk about that a lot. But generally speaking, the vast majority of electricity can't be stored, and therefore has to be supplied at the same time that it's demanded. And that one fact leads to a lot of implications as to the way that our grid was formed and operates. Okay. And so in contrast with other things like gas or water, where we can store them, that lets those utilities kind of get around a lot of the timing restrictions that we have, that electricity has to deal with, right? So there isn't like a CAISO for water or for gas, because they don't need to care about, oh, you got to deliver all this electricity right now, and we got to turn on all these things right now and turn off these things, right? And so this one fact is a pretty unique thing about our electricity system, that makes it very challenging to operate. Okay, and so yeah.
You mentioned that like the electricity made by one power plant is the same as electricity made by another power plant.
Yeah.
How do we find and then express the value of the location of that electricity?
Yeah, so that's all totally artificial. And there are constructs in which we will do that. And a lot of this class is going to deal with that type of question. But we need to separate this idea of like attribution of how do we measure things at locations, and how do we attribute electricity production from one source or another, and impacts from one source to another. All of that is like made up. It's like constructs, right? And I say that because you can't actually physically measure that an electron was produced at this plant and ends up here. It's not physically
It
possible.
doesn't have an identity.
Yes, yeah, exactly. So we care about those things that you're talking about a lot, right? We care about the fact that electricity is coming from this particular source and is going here, and we care that the impacts of this thing, of using electricity here, is coming from this thing. And we're gonna have to jump through a lot of hoops and wheels and assumptions to like figure that stuff out. But at the end of the day, like all of that stuff is technically made up, okay? Because physically you can't actually measure that. And yeah, we'll get into a lot of that, I think, more towards the end of this course. But it is important to keep in mind that this is very much akin to like if you have like water in pipes, right? You would not be able to tell that a drop of water came from this groundwater resource and ends up in, your shower or something like that, right? You simply wouldn't be able to track that as they kind of get mixed up in the system. Okay, yeah, and so kind of to emphasize my point here about the supply and demand kind of needing to match in real time. So yes, there is storage, right? And so batteries do exist, but just to give a sense of scale, in the United States, you've got about 26 gigawatts of battery capacity. When we usually talk about like at the grid side, like 4-hour batteries scale, and so 26 gigawatts that might last for 4 hours, whereas the total U.S. power capacity is something like 1,300 gigawatts, right? And that has to operate kind of continuously.
Gigawatt hours?
power capacity means amount of electricity that could be produced at any given point in time. Yeah.
I was thinking
Yep. So this is very easy to get confused about, and this is like one of the number one things that we'll need to get pretty comfortable with in class. Capacity refers to power, in that I can produce this much power instantaneously. So if all the power plants in the US were to turn on all at once, and we assume that's during the day and all your solar and all your wind is maximally on, you would get about that much power out of it. And if everything were on for 1 full hour, then you would have produced 1,300 gigawatt hours of energy. Does that make sense? Yeah. The batteries part, I will say, is like the most confusing and kind of my least favorite thing to talk about with capacities, because when we talk about battery capacities in a non-power systems context, even for someone like me who does a lot of EV stuff, we think about the amount of energy capacity that the battery has, right? And so like a car has 100 kilowatt hours, right? But when we talk about batteries on the grid, everything is kind of in reference to other power plants. And so we talk about the power production capability of those batteries. So 26 gigawatts of batteries out there means that if you were to turn on all those batteries at once, the amount of power they could produce is about 26 gigawatts. The energy capacity of those batteries would be, since they're 4-hour batteries, it'd be 4 times 26. So you'd have approximately 104 gigawatt hours of energy capacity stored in those batteries. Yeah. Don't worry if you're confused now. We're gonna hammer this in throughout the entire course, so you guys will be comfortable with it by the end. Okay, and yeah, that's kind of it for today. Main things: energy versus power. Again, this is something that we'll drill down on throughout the class. Scales matter, and so I provided some context in those 2 slides, but I think a lot of this is just going to come from ingesting a lot of this material through experience. We're going to be mainly thinking about like kilowatt, megawatt, gigawatt, terawatt scales when we think about our power systems. Energy sources and conversions. This is stuff to keep in mind as we think about how and where the energy comes from. Yeah, electricity basics. I think, again, the easiest thing to think about here is the sort of water analogy. That for most of what we talk about, you can fall back to that, and it should translate pretty well to what's actually happening in the electricity system. Yes, and then the aspects of electricity that make it really unique, that it has to really balance supply and demand in real time, and that one fact really drives a lot of why the system is what it is today and drives a lot of how it operates today. Okay, so that's it for today. On Thursday, we'll jump right into, we're kind of moving through the infrastructure of our electricity system, from the way the power is produced to the way it's transmitted long range, and then to how it's distributed at our kind of local scale. That's kind of what we're starting out the first couple weeks with. So for this week and next week, we're going to be talking about all the things that produce electricity, starting with our traditional fossil fuel plants next time. And then the last thing that I'll mention, you guys will see it on the syllabus. We actually got a cool kind of field trip to the the UC Davis local substation, which is operates independently of PG&E. We're actually on a UC Davis campus itself is operates with a different utility, and so that'll be a cool thing to look forward to. We'll get some hands-on experience with distribution infrastructure. That'll kind of line up with our the timing of our distribution infrastructure lecture. Okay, any questions about any of this or about the rest of the class? Yeah.
Will we be getting anywhere towards understanding what levelized avoided cost of electricity is? 'Cause
Yeah, so-
I'm trying to get into it, and it just requires understanding like a little bit of a stack of energy economics that I couldn't really
Yeah.
figure out.
Yeah, we will cover energy economics topics like throughout the class. So yeah, we'll definitely touch on that. Cool. Anything else? Yes.
Are you going to make these slides available?
Yes, I'm gonna post them on Canvas right after.
Levelized cost.
Yep. Anything else? Otherwise, have a good evening, and I will see you guys on Thursday.
So what's it, levelized avoided cost of electricity?
Avoided.
We're like avoided cost of